Let's explore space complexity relationships. In this module, we will understand the fundamental connections between space bounds in computational complexity theory. We'll cover Savitch's theorem, which deals with spacetime trade-offs, and the Space Hierarchy Theorem, which provides separation results. Here's Savitch's theorem. For any function f of n which is greater than or equal to log n, any language that can be decided by a non-deterministic Turing machine in space f of n can also be decided by a deterministic Turing machine in space big O of f of n squared. In simpler terms, if a problem can be solved using a certain amount of space with a non-deterministic Turing machine, then a deterministic Turing machine can solve the same problem using at most the square of that space. The key insight behind Savitch's theorem is the idea of recursive path finding. Instead of exploring all non-deterministic paths simultaneously, we can use a divide-and-conquer approach to check reachability. This approach is embodied in the Canyield algorithm. Let's examine the structure of the Canyield algorithm. The algorithm is defined as def Canyield taking input C1, C2, and T. If T equals 1, this represents our base case where we check if configuration C1 can reach C2 in one step. Otherwise, in the recursive case for each mid-configuration in all configurations, we check if can yield C1 mid-configuration T integer division 2, and can yield mid-configuration C2 T integer division 2. If both of these calls return true, we return true. Otherwise, we return false. The Canyield algorithm efficiently determines reachability by recursively dividing the problem into smaller subproblems. Let's analyze the space complexity. The maximum recursion depth is log t, giving us big O of log of 2 to the power of f of n, which equals big O of f of n. Each level stores big O of f of n space for configurations, giving us a total space complexity of big O of f of n multiplied by big O of f of n, which equals big O of f of n squared. The Space Hierarchy Theorem states that for any space-constructible function f of n, there exists a language that can be decided in space big O of f of n but cannot be decided in space little o of f of n. In mathematical terms, space f of n is a strict superset of space little o of f of n. The Space Hierarchy Theorem is proved using a diagonalization technique. Here's the algorithm. Def diagonal language with input x. We simulate machine m sub x on input x. If we can simulate x within the space bound of x, we simulate x on x, negate the result, and return that value. Otherwise, we return false. Let's summarize the key results. Savitch's theorem tells us that in space of f of n can be simulated in space of f of n squared, leading to the conclusion that space equals in space. The Space Hierarchy Theorem tells us that more space allows solving strictly harder problems. Formally, space of f is a strict superset of space of little o of f. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.